So, have you ever tried to take a coin and balance it on its edge? It's really hard. I'm not gonna be able to do it. I don't think my table's flat. It's so hard. Anyway, take the same coin, spin it, and it stays upright. Okay? Why is that? The spinning object will stay upright when a non-spinning object will not. The answer to this is angular momentum. Okay? So, let's talk about the law of conservation of angular momentum a little bit more. We're going to get a little bit deeper into the calculus of this. Law of conservation of angular momentum. I'm going to focus on some details I didn't focus on last time, but they are critical details. We said here, one way to phrase this was Li is equal to Lf of the system because the net external torque was equal to 0. And we got that through parallelism with our linear momentum argument. But I want to rewrite this a couple of different ways. Another way to say this is delta L is equal to 0. Right? But I'm going to focus on something we didn't focus on last time, and I'm going to put the vector sign over this. Because that's the critical answer to the question from before about why spinning objects are able to maintain their balance. Now I'm going to rewrite this in yet another way. If L doesn't change, that means it doesn't change over time. So I can rewrite this as dl vector dt is equal to 0 if the net external torque is equal to 0, right? dl dt is equal to 0. So what does that mean? That actually means two things. It says the amount of angular momentum is constant if the net external torque is 0, but it also means the direction of L is constant in that same perspective. So when you spin something, like let's say I spin this like this, I spun it like that, so it has an omega like this, it has an angular momentum vector into the table. That if there's no net external torques on this, which apparently there is because we did see it changing, right, that not only would it remain spinning the way it was spinning, but also that angular momentum vector would remain in the exact same direction absent a net external torque. Okay? So things that are spinning are easier to do that because you need torques in order to change not only how fast things are spinning, but also the direction things are spinning. And if it's spinning such that, let's say its angular momentum vector is up, then it's going to keep spinning along that axis. And that axis is going to remain upwards. That's why tops don't topple over. That's why dreidels spin the way they do. Now, if you ever, a more formal version of this is a gyroscope, right? A gyroscope is just a heavy top, has a really large moment of inertia generally, right? So that means that the angular momentum is very large even at small omegas, and that allows it to stay there. Right? So the reason why spinning things don't want to topple over is because the direction of their angular momentum is preserved in the absence of net external torque. So what's generally providing an external torque? Two things. One, kinetic friction if the object is moving along with the ground, and two, gravity. But if the top is perfectly upright, I'll show later that gravity wouldn't be a net external torque. All right, but we'll get back to that, and then I'm going to attach some videos to this so you can see some fun demos that normally I would do in class. But I want to get back to a little bit of calculus basics. I said before in the last video that L was equal to R cross P. And so this was the equation when we were trying to figure out the angular momentum of an object that's moving linearly, right? Angular momentum for an object moving linear, where R is the position vector from the axis of rotation to where that object presently is. Well, notice here I took a derivative. I'm going to do that with this. It's just for fun. Why not? Well, my type of fun. So dl dt is equal to, that's a multiplication. I've got a product rule here, folks. That's dr dt cross p plus r cross dp dt. All right, so let's talk about this. Oh, okay. Dr dt, well, that's just the velocity. So that's the velocity of the center of mass cross, well, that's mass times the velocity of the center of mass, right? Interesting. Plus r cross, dp dt. Have we ever talked about that? What's the rate of change in momentum? Oh, that's net force. Okay? That's net external force right there. So we said prior F net external was equal to dp dt in our momentum unit. That's why dp was equal to F net external dt, integrate both sides, and that's where we got the impulse was equal to the integral of force dt. Right, so just a little side reminder there. So let's look at this. Oh, hold on a second. I have VCOM cross VCOM. Let's talk about the cross product. The cross product is maximized when theta is equal to, well, hopefully you said 90, right? A cross B is also equal to, actually, let me do this down here. A cross B, or the magnitude of A cross B, is also equal to magnitude of A, magnitude of B, sine of theta, where theta is the angle between A and B. Well, by definition, the angle between VCOM and VCOM is going to be 0, so I'm going to have AB sine 0, and so that's always going to be 0, so this entire term zeroes out. So I have dl dt is equal to r cross f. Oh, r cross net external f. Oh, that's literally net external torque, right? So there we go, that the rate of change of the angular momentum vector is equal to whatever the size of the net external torque is. So if there is one, L is changing in either amount or direction, some way, in the same way that as there's a net external force, the momentum of an object changes. Okay, so what does that mean for us in terms of this? Well, let's picture a top. Here's a top that is spinning along this axis, boom, boom, boom. Okay, here's your force of gravity going straight down. As long as your top is perfectly balanced up or down, then, and this is the normal force, right? Here's your pivot point, because that's the point about which it's going to go. This top has no net external torque on it, because there's no torques on it. And therefore, this top will continue to rotate around that axis. But like surfaces are not perfect. A breath of wind could come along and shift this top over to the side. The second this top is an, oh, what is that picture I just drew? Oh my God, that was terrible, right? I'm drawing a triangle on its side and I couldn't do it. That's so much more exaggerated than what I wanted, but there it is, right? Here's the rotational axis. Here is FG. Here is the pivot point. Notice here, R cross F, that let's say this top is rotating like this, meaning that the angular momentum vector is like this, okay? R cross F is the net external torque. R cross F, that's going to give us a torque out of the page. So what happens to that top? Well, you may have seen that when a top goes off to the side, let's say that the top is rotating like this, around like this, that when it's on the side, that as it's rotating like this, what actually happens is the axis of rotation itself rotates. That's due to this torque, right? This torque would be out of the page, meaning if the net external torque is out of the page, dl dt is out of the page as well, meaning that there's an addition to L, or L is changing in this direction, meaning that that thing is going to have to rotate about a new axis. So even as the top rotates about this axis, the rotational axis rotates in a circle, right? And so you've seen that motion where it does this. Once again, I've attached some videos to this so that you can see it. That motion is called precessional motion. It's when the axis of rotation itself rotates due to a net external torque on a rotating object. Or actually, the motion is known as precession, so I won't put it in its other form, precession. Okay. And it's super interesting is why tops do that. There's a lot of real fun applications to that. Believe it or not, large system that rotates, the Earth, the axis of the Earth, which is tilted, rotates. The Earth's axis points at the North Star, which right now is Polaris, but the Earth's axis rotates every 27,000 years. That's the precessional motion of the axis of the Earth. It's 54,000 years. So when the axis is pointing in almost the exact opposite direction, the identity of the North Star will actually change. In a couple of thousand years, not a couple, but like tens of thousands of years, the North Star will be pointing at another star called Vega. So Polaris is not always the North Star, it's just presently the North Star. And so that's precessional motion, and that's the vector nature of angular momentum conservation that I wanted to talk about.